Hello and welcome to physics video Fluids.3a. In this video we will discuss how to calculate fluid flow rates as well as how to compare flow rates as a fluid goes through a tube of varying sizes. We will look at this from the perspective of conservation of energy. When fluids flow, we can break them into two main types of motion: streamline, also known as laminar, or turbulent flow. If the flow of a fluid is smooth, it is the streamline or laminar flow, which is shown here in picture A. The fluid seems to move in layers, as shown here by the lines and in this picture. And each of these layers seems to have an increasing speed to it. If we were to look at a laminar flow in a tube, which we will do shortly, a picture of anyways shortly, then the flow speed will be around 0 at the walls of the tube or pipe, and it will be a maximum near the center. Above a certain speed, however, this laminar flow becomes disruptive, and it becomes turbulent, which is what we see here in picture B. Turbulent flows have eddies, these areas of disruption here, and the viscosity of the fluid is much greater when the eddies are present. So remember, viscosity is how much of a flow the liquid has to begin with, or the fluid has to begin with. These eddies complicate things greatly and make it very difficult to calculate flow rate and really to characterize the flow, because it's sort of getting quite chaotic there. So as a result, we're typically going to stick to looking at the laminar flow in this class. So when dealing with laminar flow, we need to consider the fact that the density of the fluid could influence the flow of the fluid. If we consider the amount of mass of the fluid flowing through a container, we are talking about something called mass flow rate. So we're going to look at this container here. We're going to look at the rate of mass flow, and we represent that with mass flow rate being the amount of mass we measure per time. If the density of the fluids is not changing, then we can change the mass to say that, well, remember that density is mass per volume. So mass then is density times the change in volume over the change in time. So this can tell us how much mass is going through a particular area. Now let's start on the left-hand side of this container. On the left-hand side here, our volume, our change in volume, is going to be our surface area times the length in which the fluid is flowing. So we can write the mass flow rate for the left portion here. I'll call this delta M1 over delta T, to be rho A1 delta L1 over delta T. Now, similarly, we can make another flow rate, mass flow rate, on this second side of the container, on the right side, and then delta M2 over delta T would be density over here. And for the moment, I'm going to call this rho 2. So I guess I should call that rho 1, just in case they do actually change here, times the cross-sectional area A2 times delta L2 over some sort of amount of time. The flow rates at any 2 points must be equal as long as no fluid is being added or taken away. So that means that delta M1 over delta T must equal delta M2 over delta T, which means then that rho 1 A1 delta L1 over delta T must be equal to rho 2 A2 delta L2 over delta T. Keep in mind that delta L over T is a speed, a velocity, in fact. So we can then change this equation to say that really what we have is rho 1 A1 V1 is equal to rho 2 A2 V2. This equation of continuity is what we are looking for when we're thinking about fluids going through a container. There has to be continuity between one side of the container to the other, no matter the shape, as long as fluids aren't escaping through the side somewhere. Now, since most fluids don't actually compress with pressure, we often can assume that the densities are the same in the 2 different sections or the 5 different sections or however many we have. So this equation of continuity can be slightly varied by saying that the 2 densities are the same. So then we are really saying A1 V1 must be equal to A2 V2. This leads us to be able to conclude that as the pipe gets wider, the fluids flow more slowly, or as the pipe gets skinnier, the fluid flows faster, as you can see here with the 2 vectors shown for the velocities. This might be a little bit opposite of what you're thinking would happen, but when you have more space for the fluid to flow, it's going to do some meandering somewhere, as if it's got to be confined to a smaller space, it's going to go significantly faster. But a fluid can also change its height if we have a container like this one. When things change their height, remember, they also change their potential energy. So the potential energy at the left side here will be different than at the right side because, keep in mind, potential energy is mgh, and here your h is going to be y2 minus y1. Okay, so the fluid has changed its potential energy, but it's moving. It has a speed to it, which means that it must also have a kinetic energy. And remember, kinetic energy is 1/2 mv squared. And recall back to thermodynamics, which we did earlier in the year, that there's also another type of energy that comes into play here when dealing with pressure, and that is the energy due to the pressure and the volume. So we also have a thermodynamic energy of PV, where in this case the V is pressure. We put all of this together, and according to what we just said, there has to be some continuity here because the fluid's not going out of the pipe anywhere, and we end up with all of the energies added together, PV plus 1/2 mv squared plus mgh equaling a constant. If no fluid is flowing out of the pipe anywhere except the ends, and nothing is being added anywhere except at the very beginning of the pipe, this is going to be true. Now again, it's easier to consider fluids based on their densities rather than their masses. So if we divide everything through here by volume to change it to being in terms of densities, what we end up with is that P plus 1/2 rho V squared plus rho GH is equal to a constant. Now keep in mind that these 2 constants are not the same constant because one is divided by V, but we can still look at it as a constant. This is true within one section of our pipe, but if I want to talk about not just one section of the pipe, but I want to compare section A at the lower level to section B at the upper level, then what I really need to be looking at is keeping in mind that equation of continuity. What's true at the beginning must be true at the end. And so we put this together and we say then that P1 plus 1/2 rho V1 squared plus rho GY1 is equal to P2 plus 1/2 rho V2 squared plus rho GY2. This is Bernoulli's equation. It was a relationship that Bernoulli discovered when he was doing some experimentation with fluids, water in particular. The one thing that this big equation tells us is that as the speed increases, the pressure decreases. And that, along with what we had talked about in the previous screen, that as the pipe gets wider, the fluid flows more slowly, gives us a really good understanding of how fluids work in pipes and in areas of pipes. So let's take a look at some applications of where we would use Bernoulli's equation, or Bernoulli's principle, that as the velocity goes up, the pressure goes down. The first place we're going to look at is looking at the speed of a fluid coming out of a faucet. According to Bernoulli's principle and Bernoulli's equation, P1 plus 1/2 rho V1 squared plus rho GH1 should be equal to P2 plus 1/2 rho V2 squared plus rho GH2. Now, the pressures that we're talking about here would be the pressure at the top, P2, the pressure at the bottom, P1. At the bottom here where we're looking, not on the inside, sorry about that. They are both atmospheric pressure, so P1 equals P2, so those cancel. The V2, we say here in the picture that V2 is approximately 0. If the tank is big enough, then we can assume that there's no velocity of the fluid at the top. So then V2 goes to 0. And what we end up with then is that 1/2 rho V1 squared plus rho GY1 is equal to rho GY2. If we want to go ahead and solve this for our velocity, well, let's see. We've got a density everywhere, so those cancel out. Subtract the GY1. 1/2 V1 squared is equal to G times Y2 minus Y1. Multiply both sides by 2, take the square root, and V1 is equal to the square root of 2G Y2 minus Y1. So we can figure out how fast a fluid is coming out of a spout simply by knowing that the top of the container has a speed of 0 and knowing the depth to which you are looking at the fluid flow. Let's look at another one. In this case, let's look at an airplane wing. The lift on an airplane wing is due to different air speeds and pressures on the two surfaces of the wings. Let's call the top surface, surface 1, and let's call the bottom surface, surface 2. So again, if we start with the Bernoulli's principle and Bernoulli's equation, P1 plus 1/2 rho V1 squared plus rho GY1 is equal to P2 plus 1/2 rho V2 squared plus rho GY2. Well, in this case, when we're talking about wings of planes, we can actually make the simplification that Y1 is approximately Y2. In other words, from the ground, from where you would be at the 0 point, there's really not much of a height difference between those two. So we can then get rid of these two terms because they're going to cancel each other out. And we can end up looking at the difference of pressures, and P1 minus P2 turns out to be 1/2 rho times V2 squared minus V1 squared. So the difference in pressure between the two edges of the airplane wing are proportional to the difference in their velocity squared, in the speeds of the fluid going around the air. You can use this calculation to figure out how much lift an airplane's going to get, and therefore how quickly it's going to take off or land if you're going to be starting to change the direction of your airplane wing. All right, let's look at a few more. On the left here, we have a sailboat. And the sailboat can move against the wind by using pressure differences on each side of the sail and using the keel, the center piece that goes underneath the water, to keep from going sideways. So you have wind coming down, wind being in air, so that's your fluid. And when you turn your sailboat and you're looking at the sail, not the boat itself, the force of the wind is going to push the boat to the left. The opposing force from the water is going to push it sort of towards the right, but up a little because that's the direction you're trying to follow. So the resultant force is going to push the sail towards the upper left-hand corner. Similarly, when you throw a baseball, you can get a really good curve to occur on your ball if you get your ball spinning. If your ball is spinning, it results in air speeds on the two different sides of the ball not being equal because you have a difference in shape. So just like as if it's going in the tube, this velocity of the ball is going to be working against the velocity of motion, the direction of motion. So you're going to have a smaller speed on the A side than on the B side. A couple more here. On the left, we have the back of a person's head and shoulders. A person with constricted arteries, like seen here, will find that they may experience a lack of blood to the brain as blood speeds up to go past this constriction. And again, when it speeds up, the pressure decreases. When this occurs, you can get faint and possibly pass out. But that's because, again, the blood trying to get through there is going to go faster. Now, if we look at this little hedgehog guy, here, he's hiding in his burrow. The air flows across the top of the burrow down here and up here. And those two openings provide the needed circulation to the underground burrows because, again, as air flows, there will be less pressure. So that allows some air to come out. But if you have one entrance that's higher than the other, the airflow is going to be faster there. So there's going to be even less pressure. So it will draw air into the burrow, and then that air will come out the other side. So this is how animals can live underground with having a couple of openings to their nests without dying. In the next video, we will do some calculations on how to use Bernoulli's principle and the equation of continuity. Bye for now.